Thank you very much. Right, so we won't be able to explain all the patterns that Tomasz has explained related with reactive programming, but some of them, at least like streaming to UI or aggregate root patterns, we'll be able to explain hopefully in here. So what is the vision behind Akka? Akka has come up because of the following problems. The concurrency. We need concurrency in such a way that it will not lock the system. So the system will still carry on actually processing and the system will not stop, right? That's the main problem in traditional programming softwares actually, because we deal with threads and we deal with synchronous programming mainly. Whereas what we need is actually fire and forget. We need asynchronous programming. We actually need to fire an event and forget about it and just wait for a reply, right? And we also need a scalable application which can scale up or out, which means that scale up is in the sense of like you have one machine and you put multiple hardware, whereas scale out is you do parallel programming. You have parallel distributed networks and distributed machines, and it's based on the load balance. You apply load balancing algorithm, and based on that, it routes to the correct available machine. So we need something like that, and we need that by design distributed. So we need actually multiple processes distributed inside the network, and based on load balancer, we'll pick the system will pick the correct process to implement the algorithm. And the biggest problem, in my opinion, is the fault tolerance. In none of the applications that we deal nowadays, we we give tolerance to the faults. So generally, when there is a fault, a failure, the system mainly stops, right? And it goes to maintenance, the support team. Support team actually deals with it, and the system cannot actually heal itself. So what we need is actually systems that can self-heal, right? But this is not enough. We actually need more vision, and we need, aside from all these, in addition to that, we also need all these systems to be high performant. So, for example, we need good CPU utilization, a good routing algorithm behind the distributed network, behind the scalability, and also the processes that are distributed inside the network should have small memory prints, right? So they shouldn't capture a lot in the machine, right? Those processes, and we also need elasticity and decentralized systems, which means that based on the overload, for example, during the non-peak, off-peak hours, we don't need to actually boot up all the processes inside the network. Just a few clusters are enough, right? But when there is an overload, let's say someone has introduced a new fancy feature, actually a brand new feature inside the application, so that actually getting most of the loading from the clients. So it needs to be adaptive. Based on the feature and based on the peak time, the cluster needs to adapt itself and actually increase the processes or decrease the processes, right? So to be able to implement that, we need adaptive cluster management, we need load balancing, and we need routing as well. So these are the visions behind Akka, and for all of these, there is one solution, which is Akka, which Akka deals with all of these problems, and that's the main paradigm behind creating Akka. And if you enter the Akka website, you'll see that this is their tagline to introduce Akka, what it does. It builds high-performant, concurrent, distributed, and resilient, which means fault-tolerant, message-driven applications more easily. We'll actually explain all of them one by one, what it means and how to do it easily. So, let's start. The problem is, if you look at the traditional software projects that we are working on, apart from business logic, we also deal with immutability, and threads, locking those threads, using reinterrupt locks and things like that in Java, and block the entire system while processing that. We try to use concurrent collections so that synchronization doesn't become a problem for us. and we need to notify the other threads about something that happened in one of the threads actually. We use features and things like that. So we all deal with these kind of complex software, patterns, which actually loses us the concentration about the business logic. So what we need is actually, we shouldn't think in terms of all of these stuff, all of these advanced programming techniques. We only need to think about how messages flow in the system, and by thinking about only that, we also need to have high CPU utilization, low latency, high throughput, and also scalability. All this comes for free as part of the model in Akka, and you don't deal with any of these. You just concentrate on your business logic, and all the rest is managed. All these additional features is actually coming as free as part of the Akka's model. And also, in my opinion, the unique feature of Akka is its proven and superior model for detection and recovering from errors. So when there is an error happening, the system doesn't fail entirely. It just heals itself. It retries, restarts, tries various techniques actually to be able to carry on processing, so that client doesn't recognize the failure in the background. So we'll come up, hopefully, if the time permits, we'll actually try to explain this as well. But in my opinion, that deserves its own seminar. But I'll try to wrap up as quickly as possible about error handling in Akka. So how can we achieve all of these? In order to be able to do all of these, first of all, we need to change the approach that we are doing the program. We need to think in terms of actors. So what's an actor? An actor is Akka's unit of code organization. So you try to divide the algorithm as much as possible, so that you actually apply loose coupling, and you implement the bits and pieces in your system by using actors, right? We'll come to that, what actor means soon. Actors helps you create concurrent, scalable, and fault-tolerant applications, which is the main ideology behind Akka. So with the help of actors, you start creating, you create concurrent, scalable, and fault-tolerant applications. Actor is a model for organizing your code that makes you only concentrate the business logic, and you don't deal with anything else, like anything related with system level. So you just program at a high level. You can see actors as nodes in cloud computing, right? Which actually is encapsulated and decoupled from each other. And they have their own, these actors, they have their own memory and behavior. So, so the state is captured inside an actor related with that part of the algorithm. And also it has its own memory capability, memory storage capability. And it communicates with other actors asynchronously without blocking the system. Right? So how does that happen? This actor receives a message, sends that message, breaks the message into multiple messages, sends that message, forwards that message to another actor. But in the meantime, it carries on, processing. Similarly, this actor is not blocked. It actually carries on blocking, the implementation. It's actually asynchronous. So therefore, everything is actually carrying on. The system is never blocked. And all these actors carries on dealing within their processes, and nothing is blocked. The good thing about Akka is it's elastic, which can grow or shrink based on demand. So for example, if the system receives lots of messages, there should be a mechanism behind this where it should grow the number of processes, actors, so that the system can still handle this overload, right? So what happens is the Akka investigates all these number of messages and starts growing based on the demand. So the actors grow based on demand inside the network, right? And one by one, the messages are consumed. And while the messages are getting consumed, Akka also kills and maybe sleeps down the unnecessary actors inside the network, so that CPU is still high utilized and the memory is not used unwisely. So where to use these actors? An actor can be an alternative to a thread. So for example, generally what we do, especially in financial sector, when we need to deal with concurrent programming, I mean we need to actually increase the speed or utilize the CPU, we are dealing with multiple threads. So we open up new threads, and then those threads concurrently actually deals with business logic, and then replies back to the client actually based on the outcome. But we don't need to think about threads anymore. An actor is an alternative thread. It can be an object instance or a component which is containing the service logic. So for example, let's say you have a service class where you implement your business logic and returns a result to the client. You can actually use actors for capturing the business logic. It can be a callback or a listener. It can be a promise. So for example, you may receive a reply, and based on that reply, the actor can be initiated, and the actor can come to live and start processing, and then and forwards that message to something else. So it can be a callback. I also explained that single thread service, or it can be a router, load balancer, or pool. So Akka already provides you load balancing techniques or routers, but if you want to implement your own custom routing logic or load balancing logic, you can use actor for that custom load balancing algorithm. It can also be used for finite state machines. So for example, you are in a state, but you receive a message, you process that message, and now you want to change your state. Akka actors can become a different state, or can unbecome from a state. There is actually a separate concept in Akka called becoming and unbecoming. Hopefully, if time permits, I'll come to that. I'll try to explain how we deal with becomes and becoming and unbecoming to a different state. What are the capabilities of an actor? It can process an algorithm like I explained before, or it can store data like my friend Tomasz has explained. It can store the events and the coordination of those events as well to actually replay when there's a failure, or it can store the data that's customer specific into its own database, or it can communicate with others. It can communicate with other actors by sending messages, forwarding messages, getting replies from those actors. What to do with message? When an actor receives a message, it can either create another actor within the hierarchy, like for example, let's say this is our hierarchy of actors, and I'll explain, but this is the aggregate root actor, which is managing all the children actors. When let's say this actor receives a message, what it can do, based on the type of the message, based on what the rule book says, right? It can create another actor inside the hierarchy, and it can actually delegate that work, that algorithm, to that actor so that it can do something else, right? Or when an actor receives a message, it can forward that message to another actor that it knows. So inside the network, each actor knows each other, based on their namespace, and it can forward that message so that the business logic or the process, the algorithm is delegated for another actor, right? So if we play this animation, what happens is this actor forwards that message to some other actor inside the hierarchy, and that actor, second actor, plays the message. Or it can create another message, transform the message, create another message, and send that new message to another actor that it knows. So when a message is received, actor transforms that message into another message and can actually send that message to another actor so that that new message can be processed by the second actor. The last thing that it can do is all these stuff that I explained to you, sending, forwarding, creating actors, are actually in my terms, it's the rules book of that actor. So there is, you'll see shortly in the code as well, it actually applies pattern matching, and based on the pattern matching, it deals with the message, right, in a nice technique. So based on the rule, it can either forward the message, create another actor, or it can forward the message to another actor, or based on the pattern that it matches, it can actually create a new message and then sends that message to another actor inside the hierarchy. So what are the main actor operations? The first actor operation that I already described to you is defining the actor, right? Creating the actor. So defining the rules book, sorry. And the second operation is the creating the actor. The third one is sending message to another actor. The fourth one is supervising, which is used for fault tolerance, right? And hopefully, time permits, I'll explain this as well. And the fifth main operation is becoming. So an actor can change its state to something else, right? And define a new rules book for that new type to actually deal with the next set of messages, which is generally used in final state machines, right? But we won't be able to cover that. So today we'll be covering those three, optionally supervising technique as well. So let's start. How do we define an actor in Java? First of all, because it's a message-driven application framework, you need to have your own messages. And all these messages obviously needs to be serialized because it will be going within different JVMs inside the machine, so it needs to be serialized. In this particular case, the actor that we'll be defining will use this greeting message and will respond to that message, right? So what happens is, we define the message the actor will be responding to, and now it's time to create the actor. And in this particular case, our actor is responsible for greeting to someone who sends the message to this actor, right? So it actually, what happens is it receives, this is Java 8 by the way, so we are using lambda expression here, and we actually define the rules book, like I said, and the pattern matching inside the constructor, which is a new technique. There is an older technique which wasn't available, which was available before Java 8, and that was extending from an untyped actor and overriding on receive method. But now we don't need any of this. We just, simply define our patterns inside the constructor by actually passing our own function to the receive method, right? So what happens is, if this actor receives a message of greeting type, it will just say hello to the person that is sending this message. So this is what this actor is responsible for. We define the actor class, and we define the behavior, which is the rules book. The Scala version is though, right? Because in this seminar, hopefully we'll cover both the Scala and Java 8 versions, and I'll give the judgment to you, so you can decide which one is better. I have my own opinion, but I won't say it. So this is how you define a message just by using one-liner, right? So you actually create a case class, which implicitly creates the constructors, the getters, setters, and toString and all these equals methods. And you use multiple inheritance here. Actually, that was called something else, but anyway. So you use you actually create your greeting actor by extending from actor, but you also use another trait to actually be able to log the outcome of the received message, right? The process of the received message. So what happens is, you actually override the receive method, you define it, and you apply pattern matching, and you actually get your greeting message, and you capture the attribute inside the greeting, and you just say hello to that person. The second main operation is the create. And what create is doing, like I explained before, it actually creates a new instance of actor. It's extremely lightweight. Every actor is just a couple of, a few bytes, and it's extremely lightweight objects, and it encapsulates the state and the behavior. So you don't deal with whether my object is immutable or not, because when you make a request to another actor, you can't see the state of it. What you get as a reply is a reference to it, right? You don't deal with the objects, the object itself, which I'll come. So all these actors are, which I'll come to that point actually, but all these actors are immutable, like I said. And only way to check their state is to send a message to that actor to ask for its state, and you receive a reply which contains that that actor's state, implicit state. How do we create? Right. This is what we have seen. So we will not be covering that. So we created the message and we create the actor. But how do we create an instance of this actor, right? To do that, first of all, you need to create the hierarchy of actors, right? In this case, the very top actor on the top of the hierarchy is called guardian, right? So you have to first create the guardian actor. For that, you need to create the Akka actor system, and you need to give it a name, right? So the name of my hierarchy will be my system in this case, right? And to be able to create is the first level of inside the first level of the hierarchy of actors, you just use that guardian actor, which is system, and you say actor of, actually there are bubbles already, you create an actor system, and the actor system creates this actor for you, which is actually greeting actor. And you also can give additional configuration for that actor. For example, if you want that actor to specifically live inside a machine within the network, you can mention the host name or the port number of that machine, so that that particular actor can live inside that machine or series of machines within the network. So we won't be going into those details, but you can give extra additional properties for each and every actor. You need to give it a name. You need to give a name to actor so that it will have its own namespace. What is a namespace? I'll come to that soon, hopefully. But every actor has to have their own unique namespace so that they can be selected by other actors, right? What you get is an detached copy or reference of the actor. Therefore, you don't need to think about whether I actually expose my state inside that actor or not. You just get a reference to that actor, and there are some predefined methods inside that actor that you can send messages or forward messages, right? And you cannot, for example, let's say the greeter had a private variable here, let's say recipient, okay? You won't be able to say greeter.getRecipient because there is no method like that. So therefore, you don't need to worry about whether I provided setters, I made it private or public and things like that, right? The Scala version of this is simply, because it's a case class again, you don't say new, you just create an actor system, and then you actually create a greeter actor reference. You actually get a greeter actor reference, and you create the greeter actor and give it a name like this, right? Which is very similar to Java. Right. What happens in the background when we run all these statements, right? What happens is, as soon as you say you actually execute this line of code, Akka system creates a guardian system actor for you, right? Which is the top of the hierarchy, which manages everything for you. And when you actually when you want to create an instance of an actor of A type and named as A, it actually puts it under this guardian, so you can reach A through guardian. Inside the actor A, if you want to create an instance of B, which is executed inside A, constructor of A, what happens is it's actually Akka system creates the instance of a B actor as a child of A, right? And it carries on, and you can do all these kind of operations, and you can create a hierarchy like this. What my friend Tomasz has said, that Akka is a good way of implementing the aggregate actor pattern inside the domain of the domain-driven design, right? What happens is the top, if you design it in such a way that you propagate, you actually delegate the work to your child actors, right? And you aggregate, wait for the results, wait for the replies from all these child actors, and then you aggregate and form a reply and send it to client. in that case, this A becomes your aggregate root. I'll actually give a very nice example of a real life case study where we can clearly see what aggregate actors is and how we can create it and how we can actually use it in real life scenarios. But in this case, as you can see, you can clearly see that there are two hierarchies here. And this left hierarchy, the left wing of the hierarchy is actually managed by A. Right? So that makes that actually becomes our aggregate root actor, and E becomes our second hierarchy's aggregate root actor. You can only reach an actor from another actor by selecting that actor using its namespace, right? Each of these actors has their own. When you start creating the actors one by one, Akka assigns them a name, right? And that's actually similar to file system path, right? So, for example, when Guardian creates actor A, its name becomes A/A/AB/ABC. Similarly, AE/EA/EAC. As you can see, A is actually used for both of them, but the uniqueness becomes in the namespace, in the path of it, right? The names of the actors doesn't have to be different, right? The uniqueness has to be on the file path, right? On the actor path. In this case, A is used twice, B is used twice, but when it comes to their namespace, they are unique. Right. As I said, that Akka can distribute all these actors inside the network into multiple machines, right? How do we do that? You can mention, you first need to actually enable the remote actor capability of Akka, and you need to actually mention which protocol you want to use, in this case TCP, and the host names, in this case just one host, which is localhost, but you can mention multiple host names and ports, and one by one, by using the JSON style, you can mention your network, right, inside the application conf, inside the configuration file, which is specific to Akka, and you place it into your meta-inf directory, right, so that Akka can recognize these configurations for you, right? So by using this remote capability, now what you can do is, let's say you are in actor A and you want to actually reach to actor B, right? You want to actually make a call, send a message to actor B. To be able to do that, you need to first select that actor. So for that, you need to mention the protocol that you are using, the system name, if you know the host name, and the port number, and the path to that actor, right? In this case, to be able to get B from A, you need to say, this is my actor system name, this is my host name, host name, this is my port number, and this is the path to that actor. And this actually gives you an actor selection object where actually you can make calls to that B actor, right? So, in order to be able to send a message to an actor, first of all, that sending operation should be asynchronous. That's the whole point of Akka, actually. You should just fire the message and forget about it. And you have your own rules book. You just wait for a reply. But you carry on processing. You can do something else. For example, you might receive 10 messages at the same time, right? All of them are different types. You still carry on processing all these messages, but in the meantime, you receive a reply from something that you had sent about, right? Let's say a reply to a message that you had sent. Akka actually cluster management creates multiple instances of that same actor and can manage can still make it non-blocking and can reply to that message while dealing with other stuff for that specific actor. So you just fire the message and you forget about it, all asynchronous, all non-blocking. All happening reactively. An actor is passive. It's not capturing anything. It's silent. It is actually waiting, sleeping, until a message is sent to it, which triggers something within the actor. So an actor may not be doing at a particular time, right? But it receives a reply and it awakens itself and it actually processes that message. How do you send? We have already captured all this, so I have not mentioned about this. So now I have my own greeting actor. And I just create a new message of greeting, which is here. And I actually say that my name is Charlie Parker. I just want a greeting from this actor system, and I just send a message by using the predefined tell function for this detached copy of the actor, right, greeter actor. If you are expecting a reply from that actor, so you may not just firing and forgetting, right? You also want a reply from that actor based on the message processing, right? In that case, in this particular case, I just want to greet. I don't require another welcome back message or something like that. Therefore, I don't need to send my reference to that new actor. But if I had expected a message from the actor, a reply from that actor, I would have actually sent my reference, my actor reference, as part of the message as well, right? Which will come to that. What happens is, as soon as we send the message, the greeting actor awakens itself if it's not doing anything at that moment, and it matches, applies the pattern matching, it matches with the type of the message, and it logs hello Charlie Parker, right? Scala version is easier. So what happens is, you can do it like this, but there is a simpler version of doing this, which is you just use the exclamation mark, say greeter, greeting, and this is my name, right? So this is the way you send messages, you tell messages by using Scala. If you want to get a reply from an actor, let's change the scenario, right? I'm a person. I'm an actor person, right? And I actually receive a message called friend, and I just want to say hi to that friend, okay, as part of that message. So what happens is, I receive a friend actor, a friend message, and I just reply back to him saying that hi, my friend, right? And I wanted my friend to know myself, right? So therefore, I also send my reference as well to that friend. We just fire a message and we forget. Whereas in Scala, you just apply pattern matching, and in one-liner, you reply back to that sender, right? You can also forward the messages. Actually, forwarding is like sending a message to an actor, but you actually specifically forward the message so that the original sender address reference is maintained, right? Even though the message is going through a mediator. So, for example, I receive a message called friend of friend. So I'm not supposed to welcome that guy, right? My friend is supposed to welcome that guy. So therefore, I just forward that message to one of my friends, which will be able to recognize him and welcome, right? Let's say. So therefore, I just forward that message to some other actor, right? I don't deal with that actor. I don't process that message, right? I just immediately forward that. Therefore, the original sender and address reference is still maintained, right? So the guy that is replying to this message will not be aware of me, right? I'm just forwarding it. I'm just a mediator. So the full picture, we can now go back to IntelliJ and compare Java version of it and Scala version of it. But I just want to skip that because the next part is more interesting, right? I'll be explaining a case study. So far, yeah, we learned how to send messages, how to actually get replies, how to forward them, but we need to put this in a context, right? Because otherwise it doesn't make any sense. So in order to make it sense, I want to apply it on a case study, right? And this case study is actually trying to show aggregated balances for different kind of account types to the client reactively, right? Which means that it will use WebSockets because that's the only way you can do it at the moment. In HTML5 application, maybe there are more ways, but that's the way we use at least, in my current project. So what you do is you make a connection to the backend and you keep the connection open and you actually receive replies through the WebSocket reactively, and the client might do some other stuff, and so it will not block the client, but the WebSocket will, when it receives the message, it can notify the user, or it can do something else. We'll come to that, right? So the client makes a connection request, and it actually comes to the service layer, and the service layer realized that there is a new client that is just logged in, right, to the system. Let's say open up the page, and the page is, let's say, show aggregate balance. The client wants to see its aggregated balance balances for all of its accounts. Let's say it's a global international client, right? It has multiple kind of account types and things like that, tens of thousands of maybe accounts throughout the world with lots of, let's say, currency pairs. You need to apply currency rate algorithms and then convert it to local currency and things like that. So let's say complicated page, right? The service layer first needs to create an actor. Let's say in this case, because in my opinion, in this case, we know the client, which is a specific customer. To be able to serve that specific customer, we need to create a connected client actor. So we create an actor just to serve for that specific client, right? So the service layer realized that there is actually a new client just opened that web page, right? And the system, to be able to delegate all the processes, business logic for the future processes, the service layer creates another actor just for that specific client, which is called connected client actor, let's say, right? And then this connected client actor, because the client wants to actually get its customer balances, service layer creates a new message called get customer balances message, right? And makes a call to connect client actor. The connect client actor realized that actually there is another system that wants to see the customer balances for this specific client, and therefore it creates another actor, which is another hierarchy of actors. In this case, account balance aggregate actor. So this will be our new set of actors where the response in which the responsibility of this aggregate actor will be to collect all the customer balances, aggregate them up, maybe categorize them based on the account type, apply currency rate conversion, and send data replies back to the connect client actor, right? So what happens is this account balance aggregate actor concurrently fires up 5 different actors. Each of them is responsible for different types of accounts, right? Saving accounts, money market accounts, basic checking accounts, interest-bearing checking accounts, and time deposits, right? So for all of these messages, a separate actor is responsible now. So the work is delegated into multiple actors. So we are trying to be as loose couple as possible, right? And all of these accounts need to now connect to a big data platform to fetch all the account balances, right? They make separate, concurrent requests. Now this is free. This delegated the job. This is free. This can deal with something else, right? Now all the responsibility is on them, and they are concurrently making requests to the big data platform. All the requests are done now. All of them are free. They can deal with something else, right? And the big data platform processes all these messages and starts sending the balances one by one to the relevant actors, right? This interest-bearing checking actor receives the balance for that account type and replies back to the account balance aggregate route. Account balance, okay, we come to that. And in the meantime, another reply comes from, and it actually sends the balance for that specific account type to the aggregate actor. But in the meantime, aggregate actor realized that the first balance that it received contains multiple currencies, right? Now it needs to convert it to local currency. Therefore, it communicates with other set of actors to get the live rates, and the live rates are retrieved from another big data platform that contains all the currency rates, right? And in the meantime, this aggregate root actor keeps receiving, the balances one by one from all of these account types, and concurrently, it actually receives the live rates from the big data platform. For all of these accounts, it receives these live rates, right? And when everything is received, now is the time to aggregate them, right? And that was the response of this aggregate actor. What it does, it actually starts examining all these messages, aggregates all balances by type, and then it sends a reply to the original sender, which actually made the initial request to get the aggregate balances with the correct set of aggregation. And it is, don't forget, this was WebSockets, right? The client is doing something else in the background, right? Let's say it's not blocked, right? So, but the backend now processed all these messages and sending a message back to service layer, and it is streamed back to UI, right? So this is the case study that I want to mention. I don't know whether I was clear, but this is, I think, one of the applicable points of Akka, especially in streaming applications like this, right? Now can I get another 5 minutes? I'm a bit late, but anyway. All right, I'll try to explain this, right? Resilience and failure management. Failure might happen, right? We can't avoid this. No matter how hard you try, there is always one more case where you didn't foresee something and therefore your test didn't reveal, right? So the question is not how can I avoid it. You will have these. You are a human being. You can't create a perfect system. You'll receive the problems, right? You'll have failures. The question is how to deal with it. How can we deal with all these failures? The way to deal with these failures in traditional programming languages like Java, C, C++ is through threads. You work with a single thread, but if this thread fails, you are screwed up, right? What you do is you can't propagate the problem between threads because you are a single thread. You don't know the other threads, right? And what you do is you start doing explicit error handling within this single thread. You apply try catches. You try to catch the exception, transform something else. All this kind of stuff that is unrelated with the business logic, right? Which leads to defensive programming, error handling mixed up with business logic, right? And you get and an if joiner comes to your project and he gets confused because it's really hard to find out what the business logic is. Akka finds a very, very good solution for this problem so that you can only concentrate on your business logic, and that is resilience. What we need is resilience, fault-tolerant applications, right? The definition of resilience is the ability of an object to spring back into shape. When a problem happens, give it some time, retry a few times. Maybe it was a temporary problem. Maybe it will heal itself. So you try to make it spring back into shape. Or then another definition is the capacity to recover quickly from difficulties or toughness, right? How can we apply this technique in Akka? We need to first find out what typical failures are, because let's see whether what our failure types are generally. Generally, they are database servers that are temporarily not available, right? Something happened and the database server went down, right? Or there's a new feature that you introduced. All your customers are, want to actually try that feature, so an overload happens in your system. Or user makes a malformed input, and therefore your system screws up, right? Because you don't handle that input. You didn't actually cover that as a test as well, right? It's something brand new, coming from live system. But all of these actually can be recovered automatically. So you don't need to deal with handling all these kind of errors. And there should be a way that system should heal up itself and go back to normal as soon as possible. So how do we do this? First of all, failure must be compartmentalized, which means partitioned, right? So you need to actually define your system as small pieces as possible. One failing component should not take down the entire system. If there is a component, let that component, manage its own failure. Do not bother the other, components. Design it in such a way that all of them are loosely coupled. The failing component should be either retried, because it was a temporary failure, let's say, or restarted. Maybe the user input was malformed, so you restart the component to get back to normal, or you initiate it to a backup system. You can't recover from it. You have your backup system. You become something else. You change your direction, actor's direction, to something else so that you can answer to that client. And all this should be automated, right? Once the component is up again, interaction with other components resumes as well. So you still non-blockingly, carry on doing stuff, and you start interacting with other components. Let's apply this quickly into our actually application, that case study. This was the last point, right? So let's say we still receive updates because the customer is doing processing, and actually a new balance is arriving to one of the accounts. So therefore, all this is connected still. Yes, we stream back to UI, but everything is still connected. The user, the client is still seeing the balances getting updated on the live, right? Because it's WebSockets through streaming. What happened is actually something happened to big data for the currency rates, right? And you cannot retrieve the USD GBP rate. And so therefore you cannot convert your local currency, which is USD, let's say, for this customer. Therefore, this currency pair rate actor is affected. And one of the messages that is actually replied back to this aggregate actor, that aggregate actor cannot retrieve the currency rate for that particular currency rate, right? Currency pair. But the rest of the live rates are still available, right? So they are available just for that particular actor. Something happened in the database and you cannot retrieve the message, right? What happens is the aggregate actor still knows what to do and starts retrying for that specific actor, retrying 5 times in every 3 seconds, right? So for example, for that USD GBP rate, it doesn't just immediately fail and send the message to the user interface. Something temporarily might have happened. So therefore, it retries 5 times. In the fourth billing, what happened is it received a success. So now, in the fourth retry out of 5, just before the end, the big data was able to return a reply for that currency rate, and therefore it unblocks the currency pair rate actor, and the aggregate actor retrieves the currency rate, and therefore carries on streaming back to UI. So therefore, we don't. To be able to make this all work, what we need to do is we need loose coupling, like I explained, plus we need parental supervision. That aggregate root actor needs to retry or restart the children actors, right? To be able to do that, we actually apply supervised strategy, and what we do is actually in that aggregate root actor, we define a supervising strategy, and then we say that try 10 times within a minute. If an exception comes from the underlying set of actors, and the exception type is arithmetic exception, you let that actor resume, because it's a one-to-one strategy. If it was all for one strategy, then all the children, even if that's not failing, most of the children are not failing, it will be resumed. It will be resumed. All these messages would be resumed or restarted. But in this case, the most common one is one-to-one, because you don't want to you don't want to block or interfere the ones that are already working. So you apply one-for-one strategy, and you just resume that particular actor. Or if it's a null pointer exception, there is something serious, we restart the actor. If there is an illegal argument exception, we stop the actor, right? So these are the different supervising strategies that you can apply for some specific set of actors, actually. If there is anything, if I can't handle this, I don't know how to handle this exception type, I escalate it to my supervisor. I escalate it to the guardian actor, or in this case, connected client actor, because the aggregate root's parent actor was connected client actor, and let him deal with this, right? Because I don't know how to deal with this. So what happens is all your try catch logic is actually captured separately in a supervised strategy pattern, right? And all your business logic is somewhere else, so you don't deal with try catches. In Scala, it's easier. I not mentioned pattern matching, resume, restart, stop, escalate. Okay, and you specifically say my maximum number of retries will be 10 within 1 minute of range, right? If you don't provide any supervised strategy, there is a default supervised strategy that is very handy for you. And what happens is it has, for each specific exception types, it already handles those exceptions by default. For example, if the exception actor initialization exception, which is happening while we are initializing an actor, it will stop the failing child actor. Or if it's a killed exception, it will stop the failing actor. If it's a compile time exception, it will restart the failing child actor. If it's a runtime exception, it will be escalated to parent actor. So that's the default strategy, but it's advised that you actually customize this supervisor strategy based on your needs, right? Because of time constraints, I'll stop here. I will not mention routing techniques, round robin routing, and load balancing techniques, which is actually a bit advanced topics, but it helps you to apply different rounding and load balancing strategies. So therefore, let's go to the last page. Hopefully, we will arrange another session, and we will be covering the life cycle of the actors, futures, which is an interesting topic in Akka, how to stop actors, how to kill actors, how to become or unbecome something else, like I explained before. Like Tomasz has explained, which is an important topic, how to do event sourcing, right, by using Akka persistence. And in addition to all of these, because we are skipping the routing part, how to do load balancing and routing. So we can capture this in the next session. And also the most important part is reactive streams by using Akka streams. So how to actually do streaming between the UI and the backend, right? There is actually a concept called Akka streams for them. So thank you very much. Thanks for listening. Sorry, I'm a bit out of time. So any QA? So let's arrange another time, 50 minutes for QA if you want. So any questions to Tomasz and me? Yes, sir.
For the big data platform, you mean it's kind of Spark or some kind of NoSQL database? What do you mean by big data platform?
I'll leave that question to Tomasz.
So what is important here? I mean, Spark is one of the more popular. There are better tools like Flink, which is more incremental, reactive. But I think what is important here is that what you get from either big data or other storage, you get these change feeds. So when we just had a discussion before, what you really want is when you integrate with those platforms in a change feed, or when you do some kind of ETL pipelines, that's something called ETL pipeline with traditional database, you want something called CDC, a change data capture. So when your data changes, you get the changes propagated to your system. So I don't know. So it's more about the way you retrieve the data, so the data stream to you, if that was the question. But in terms of the big data platform, that's not yet specified, but most likely something Spark-like, Spring, Spark, Apache Flink, and or Apache Beam, a new project that kind of treats Spring and Flink as execution engines only, and provide a much richer model for streaming and delivery. That's the project that came from Google about a couple of weeks ago, and been open sourced. So yeah.
Does it have to be big data? Okay?
It doesn't have to be. It's just in this particular case it is. But yeah, definitely doesn't have to be. Yeah.
We are talking in terms of this case study, right?
Yeah. So
okay.
just
yeah. Yes, Zach.
How large was the currency pair data set?
Sorry?
So how large was the currency pair data set?
It's a lot actually. If let's say there are 55 currencies that we are dealing with today, 55 multiplied by 54 divided by 2, something with thousands actually. Okay. Thousands of actors. So it's advised to actually create breakdown into as much actors as possible. And so therefore, in my application, in this case that I actually try to create an actor for each currency pair. But you can create just one currency pair actor and also retrieve the currency pair as a parameter inside the message. And but that might overload the actor, right? So therefore, in this example, I try to break it down for each currency pair, a separate actor.
You said overload the actor, but didn't you say earlier that it would scale out?
Yeah, there is another way. I mean, I didn't capture that part, but I'll just open this, or you can see from here. For a specific actor, you can give a boundary, right? So you can say that there will be 2 instances of it, minimum, and when the overload happens, you can increase to 15 instances, right? For that particular case, you could have 1 currency pair actor. So it all depends on the trade-off, right? Or how you want to design it. So you can either give an upper bound of like thousands or something like that, or you can actually keep them separate and just narrow down the boundaries. Another question?
So, I mean, across the actors, I can understand you pass the messages and blah blah. So, what happens inside the actor itself? For example, here you are using multiple instances of the same actor.
Yes.
So, what happens if that actor has a shared state inside itself?
No. Do you want to answer that, Tomasz?
Yeah, so the assumption is that you don't have a shared state. You don't expose shared state with
You
an actor.
shouldn't be exposing any.
You don't.
Yeah.
Even if you want to try, you can't expose. That's the main point, because actors are detached. They are not aware of each other. You can't get the state.
I mean, just in one actor instance. I mean, so here you say that you can have up to 15, for example.
Yes.
Actors. So I mean.
All of them will have
same
separate states.
instance I mean, there's one actor and there are 15 instances. of
Yes, there is one actor class, and there are 15 actor instances. All of them have separate states.
But one actor can act as a source of common state for a few other.
Well, there is no common state. They are not there. You can only retrieve the state by sending a message and getting a reply. You can't.
You can conceptually.
Yeah, you can conceptually create, model it by with parent-child relationship and things like that. Definitely, but on the design level, not on the instance level, right? You can have a parent actor. You can have children actors. I mean, design-wise, I mean, extending from parent classes, but the states will not. They will not be aware of each other states. Yes, I take it.
Thomas said that the class should know that they are connecting, right? They are sending their request. So because the state is stored in the memory, the class should know the wish node.
Yeah.
So how do you scale out in that case?
So what Kemal showed here is the Akka remoting, where you specify where you want to connect.
They're always connecting to the guardian?
Yeah. So that was, I think, within one system. I think you showed remote where it connects and specified the node. But what is important, the kind of routing to make sure that it connects. There is a library called Akka clusters, and it handles the distribution of actors transparently and handles and manages the routing. So you're not interested where exactly on which node it is.
So there is a load balancing. Or
Yeah, there is. Yeah, that's handled.
if you're storing the state on the memory on a node, and if load balancing is working, if it uses
So
another node,
then you don't know. Yes. So then, but then you cannot. You have different consistency guarantees. So you have to design the system. You know, not everything can be scaled out in this way, right? Yeah.
Yes,
How does
Faruk.
Akka translate everything onto physical resources? Does it have something internal like a source, or is it really depending on how you map it? Like one actor is one instance of, let's say, M1 large on AWS.
It's actually a process, or it can be a process within the JVM, and within that JVM there might be thousands of processes, if it's a local instance, within the same JVM you define all your actors, and so they will have their own memory prints within that JVM process. So it all depends on whether you apply remoting capability or not. But at the end of the day, if it's remoting capability, then they become separate process.
Okay, but how does that instance, let's say 1,000 like physical boxes?
It doesn't have to be thousands physical. It can be one physical box,
Yeah.
and multiple processes in it.
But I think this is also a question for the Akka clusters, where you can specify the sharding, for example, sharding mechanism. How do you scale out your actors, and how do you shard them, and which requests are routed to which actors? I think there is this mechanism for that. And then on local scale, I think there's executor that runs. So you ask for the mapping between threads and actors. So I think there is executor, and I think it's even pluggable, so you can plug in your own execution.
Hopefully, in the next session, we'll be able to cover these as well when we mention about sharding, load balancing, and Akka cluster management, adaptive active cluster management. Yeah.
Are there any figures of trends by which this technology is being adopted in the industry?
Yes, for example, I'll skip the slide, but I'll hopefully if I can find it.
In the meantime, I can say that that's not Microsoft Azure, which is the Microsoft cloud platform. They provide their, I think it's called Service Fabric, which is the programming model on the Azure, and that also leverages the actor model. It used to be called Project Orleans, now it's called Azure Service Fabric, I think. So they also use the actor model for that.
So the organizations that use Akka today is a lot actually. For example, our company HSBC is using it for the time at the moment in several projects, generally based on Java 8, but Scala as well, partially. And generally, financial institutes use it a lot because of the concurrency and the asynchronicity of it and non-blocking mechanism. But this is just a subset of it, so
Sure.
it's just
I've heard that at Credit Suisse is quite big. They've created many new teams now.
yeah. UBS, you can see, even Amazon is using it, and yeah, and it's actually used a lot in gaming sector because of the reactive programming, right? Because in multiple player applications, you need to actually synchronize the players, so streaming is used a lot there.
Another question for Tomasz. You said for disaster, if a disaster happens on a node, you are going to reproduce all
Events.
requests one by one. Right?
To another.
How do you know the order of the requests?
So the events are stored in order in the journal, in the log itself.
Yes.
Log where on
Log?
that node?
Sorry. So the events are stored in a kind of shared log.
Persistence
Journal,
mechanism.
Yeah, log or journal.
But the requests were sent to node, right? So it's taking the request and also logging.
You take a request or command, act on it, do something, and store the response into the log. The order of that is maintained within the log itself. Does that answer it?
To answer that, maybe in under a case study, right? When the connect client actor sends a message to account balance, and all these messages are sent, all these consecutive operations, as soon as they are sent to an actor, is actually stored as an event in the journal, right?
Mm-hmm.
So that if something happens, a failure happens like this, for example, everything goes down. When you boot up the system, you can replay those events, right? Up to the point that it failed, and then, sorry.
So there's a joint list of events.
Yes, consecutive set of messages
So
that are.
there should be time synchronization amongst all the actors, probably.
Yes, something like that. I mean, it's actually logging, like Tomasz said. It logs that particular scenario event inside the person mechanism so that it can be replayed. Am I right,
Temporal
Tomasz?
sequence of the events.
You know, Tomasz knows better. So
Most
You don't
probably
need
there should be somewhere a sensitive time service.
No, you just store. So there's one shared log. So when it receives a request to store event, that's the time itself. So and you don't really need time. You just what was before. You just look, the kind of ordering within the events itself.
guys, we are
What's the biggest challenge on having an Akka system? The biggest challenge. I mean, I know a few that my friends have told me. But in HSBC, what was the biggest challenge you guys have now?
it is not very applicable to apply in simple scenarios, especially in request response model. There is no point if there is no streaming, in my opinion.
If you don't have use case for the kind of reactive system, then it's kind of difficult. And very often people use that as a replacement for the Java traditional concurrency mechanism. But it's hardly to call it reactive, right? You use Akka, but not for the reactive part. Reactive goes beyond that because there's the streaming and propagation of the change. I guess it's saying that you use Akka for your system is a little bit like saying, I'm going to use threads for my application. That does not really tell you much. But when you say, okay, I'm going reactive, then it tells you richer stories, so that there will be change propagation, interactive, and so on.
And
So I think currently it's mostly used as Akka as a replacement for concurrency, right? Not necessarily having the interactive.
Yeah. So it doesn't have to be reactive. It can be any multiple threads that you are working with, you know, you can replace with Akka actually.
Do you have problems with with storage and memories? Keeping
There was a slide
different
which I
actors?
there was a slide which I skipped actually, which actually gives the performance of it and how much memory it actually captures.
No, not like that. So, what happens is that you will end up with so many different actors. At one point, all these actors will be stored somewhere. And getting these maps, because I'm assuming all these are mapped out. So you map them, you load them, you instantiate them. You have a problem with this storage, like querying this mapping storage, which could be, for what I've heard, up to 200 gig. Because if you go up to whatever Akka has provided you, it's fine. But once you start extending the basic objects and you have maps of maps, you have to load all the...
It will have its own bottleneck. I agree with you. I mean, we need to actually measure it, but when you have trillions of actors, billions of actors, I mean, obviously you'll have some problem.
That's the biggest bottleneck I've heard for this, because it's fine if you keep it simple and you're just doing a simple like Hadoop application of React.
But also it's advised to stop the actor if you're not using it. So if you finished using an actor, right? For example, in this case, client leaves, right? Client doesn't come anymore. Client left the page. We don't need this connect client actor anymore. We need to stop it. That's out of use now. That's wasted, you know. That's wasting memory. So just kill the actor. So that's also another pattern which we can capture in the next session. Last question. Yes, Haluk?
As I understand, it comes with resiliency and scalability out of the box. What about security? Does it have any built-in security features?
Security is on top of this actually, because at this point, for example, you apply the security on the service level, right? So this is used internally, and you are communicating with other systems, yes. And you need to actually apply, you know, security mechanism when you are interacting with other systems. But that's not part of Akka. That's the way you actually, you know, communicate with other systems. Like that's where you actually implement that security mechanism. In, let's say, if you are using TCP communication with other systems, there you need to apply strategy, security strategy. It is not part of. It's not actually captured in Akka design.
So passing a token, for example.
Yeah, something like that.
But it's
So,
not part of the. It's not part of the. It cannot be part of the actual. The standard abstract.
Exactly.
Actor. It's not.
Maybe there is a way, but I haven't come up so far. I would say. Did you come up with anything like that, Tomasz? Sorry.
SSL or anything like that?
Well, you can define different protocols like TCP, but maybe at that point you can configure more and give more settings. I'll actually